So here is one, solve this partial differential equation. Solve this partial differential equation. So what I have is, so from now on I am going to denote my partial differential equation as PDE. So PDEs denote partial differential equations. So I have the so called Laplace equation. So what is Laplace equation? Laplace equation with Dirichlet condition. So I have the equation of this form: uxx plus uyy equals 0, where my x varies from negative infinity to infinity and my y is positive, including 0. So this is an equation to be solved over half of the plane from y 0 to infinity and x negative infinity to infinity. Further, since this is a boundary value problem, what do I mean? That there is no time derivative here. So I need two boundary conditions. So my boundary conditions, I am going to talk about boundary conditions and denote it as BCs. My boundary conditions are as follows: f of x, so u of x comma 0 is f of x. This is from x from minus infinity to infinity, and u of x comma y goes to 0 as I have x goes to infinity or minus infinity and y goes to infinity. So what this solution says is that on the surface, on y equal to 0, you have certain value of the solution, and the solution decays as your variables go to infinity, your independent variables go to infinity. So in the far field or far away from y equal to 0, the solution decays to 0. So I am going to, so let's start. To figure out the solution to this Laplace equation, I am going to use the Fourier transform with respect to the variable x, right. So I have two variable x, independent variables x and y. This question is, for which variable should I use the Fourier transform, right. So you can see that x is varying from negative infinity to infinity, while y we only have non-negative values. So it is natural, quite natural to use the Fourier transform for the variable f with respect to the variable x. So then let us say this is my equation A, this is my condition B, and this is my condition C. So my A reduces to the following. So, well, let me just say that the Fourier transform of u is denoted by u of k comma y. Notice that the Fourier transform is with respect to x. So instead of x, I have this wave number k. So this is equal to 1 by square root 2 pi integral minus infinity to infinity e to the power negative I k x u of x comma y dx. So then my A is reduced to the following. So if I were to apply the Fourier transform and use the derivative for the derivative results for Fourier transform, I get that u capital U y y plus I k square u is equal to 0, or this is equivalent to u y y minus k square u equals 0. My B, application of Fourier transform to B, gives u at k comma 0 is f of k, where this is nothing but the Fourier transform of the small f. And my application of Fourier transform to C tells me that u of k comma y goes to 0 as y goes to infinity. So here I have an equation to solve. This is an ODE, an ordinary differential equation, with the following second order ordinary differential equation with the following two conditions. So this can be easily solved, and the solution that I get is u of k comma y is equal to f of k times e to the power negative mod k y. Notice that as y goes to infinity, the solution goes to 0, and at y equal to 0, the solution u k y is f of k. So it satisfies both the boundary conditions, and it can be checked, it is the solution to this ODE. So then I have to use the inverse transform to this function. So I have u of k comma y is f k times e to the power negative mod k y. So then my solution u of x comma y is given by 1 by square root 2 pi integral minus infinity to infinity f of, notice that if this is the Fourier transform of f and this is the Fourier transform of, let me write it in this form, f of k times g of k, where g of k is the Fourier transform of, well, so what I have is, well, I should write the other way, where e to the power negative k y mod times e to the power negative mod k y is the Fourier transform of another function g denoted by capital G. So that is what I mean by this product. So then my solution u is 1 by square root 2 pi. Since this is a product of two Fourier transform, my solution will be the convolution of the corresponding Fourier transform inverse of these two functions. So I have this is equal to f of zeta times g of x minus zeta d zeta. So this is the convolution of the corresponding two functions for which we have the Fourier transforms capital F and capital G. Now, so I have the following, that G is nothing but the Fourier transform inverse of this function e to the power mod k y, and we have already found the Fourier transform inverse of this function to be equal to square root 2 by pi y divided by x square plus y square. So I am going to use this expression here to come to the solution. So u of x comma y is y, after simplifying I get y by pi integral minus infinity to infinity f of zeta d zeta divided by x minus zeta square plus y square, where I know that y is non-negative. So this is where the solution can be left, because we do not know what is this function y f. Now we can check what happens to u of x comma 0, whether u of x comma 0 indeed gives us f of x or not, right. So check whether this is true or not. So to do that, we take the limit y tending to 0 from the positive end, because y is non-negative. So y tending to 0 of u of x comma y is this limit y going to 0 plus integral from negative infinity to infinity f of zeta y by pi times 1 by x minus zeta square plus y square d zeta. Okay. So, this will be equal to, we can see that if I were to take this limit, so let me just rewrite this integral. So, this becomes integral f of zeta limit y going to 0 plus y by pi times 1 by x minus zeta square plus y square d zeta. Now, it can be seen that this is also the delta function delta of x minus zeta. So, you need to check that in the limit y going to 0 plus, this function reduces to delta of x minus zeta. So, finally, my integral reduces to f of zeta delta of x minus zeta d zeta, and by the property of delta function, the value from negative infinity to infinity is non-zero only when zeta is equal to x. So, all I get is that this integral is f of x. So, the check is done. So, now let us look at some particular cases of this function. So, let us choose some particular cases of f and see what is the solution. So, let us say I choose my, let us say I choose my f of x. So, if my f of x is given by this Heaviside function. So, this is a constant Heaviside function a minus mod x, right. So, in that case my solution u of x comma y will be from y by pi t naught integral, this time from minus a to a. So, the infinite integral has changed to a finite integral d zeta x minus zeta square plus y square, right. So, now this integral being finite, this can be evaluated. Particularly this integral is nothing but t0 by pi tan inverse x plus a by y minus tan inverse x minus a by y, or we use the formula for tan inverse. So, tan inverse a minus tan inverse b gives me the following simplified expression. Okay. So, as far as the answer is concerned, this is the answer that I get for u of x comma y for this particular case of my initial my boundary condition. Now, suppose I were to see the curves for which u is constant. U is constant. So, which are those curves? So, which means that in this case I have that tan inverse this expression. So, I am using this expression here. So, tan inverse something is a constant, it is a constant only if I have that the argument inside 2ya divided by x square plus y square minus a square, this is another constant. Let us say this constant is c. So, this is equal to a constant, right. So, what I get is that this is also equal to x square plus y square. Let us simplify and this will become some, let us say alpha times y equal to a square, right. We can check after completing the squares that this is a circle, this is a circle, right. So, the curves for which u is a constant is a circle. So, these are the level curves for the problem. Now, another case could be that if I choose my f of x to be the delta function, then I can see that u, again I replace, which is y by pi integral from minus infinity to infinity delta of zeta d zeta divided by x minus zeta square plus y square, which is also equal to y by pi 1 by x square plus y square. Okay. So, these are some special cases of the problem. Anyway, so let us continue and look at some more examples. So, then I have another example. So, then I have another example of the integral type. So, I have an integral equation, So, I need to solve this integral equation, which is of the form f of t plus 4 integral from minus infinity to infinity e to the power minus a mod x minus t f of t dt is equal to gx. Okay. So, notice that I need to solve for f of t. So, notice that f of t appears here and also f of t appears inside the integral, right. So, I need to solve for this integral equations. Also notice that this integral is of convolution type, right. So, what I have is that if I were to choose this as my f and this as my g, you can notice that this is exactly of the convolution type that we have described earlier. So, which means that if I were to, let us say that this is my equation 1. So, if I were to apply solution, if I were to apply Fourier transform to 1, right. So, I am going to get, for the first case I am going to get f of k, where f of k is the Fourier transform of small f. So, f of k plus I get 4 times, notice that this is a convolution. So, 4 times, all I have to do is figure out the Fourier transform of this function, which has already been done in the last few lectures, and take the product of the two Fourier transforms. So, this becomes 4 times square root 2 pi f of k. So, that is the Fourier transform of this function times 2a divided by square root 2 pi k square plus a square. Again, this is something, the Fourier transform of this function is something that we have already calculated in one of the previous lectures. So, this becomes the Fourier transform of g. So, this is nothing but the Fourier transform of g of x. Okay. So, then when we simplify this equation, so let me call this as 1 prime. So, 1 prime becomes f of k, this is equal to a square plus k square divided by a square, we are simplifying. So, let us simplify and do all the calculation. I get a square plus k square plus 8a times gk. So, if we were to know what is the right hand side, we can immediately take the inverse transform and find the solution f. So, in particular my f is 1 by square root 2 pi minus infinity to infinity a square plus k square divided by a square plus k square plus 8a g of k e to the power I k x dk. Okay. So, let us now look at some specific cases. Let us say suppose I choose my a equal to 1 and suppose my g x is e to the power mod x with a minus sign. So, in that case my g k, the Fourier transform of g x is the following expression, square root 2 by pi 1 by 1 plus k square. Okay. So, substituting, so this is a special case. special case. Okay. So, substituting all these values here, let us say this is my 2, I get the following. I get that f of t is 1 by square root 2 pi integral from minus infinity to infinity e to the power I k x divided by k square plus 3 square, the 9, times of course there was this factor 2 by pi and dk. So, after I do all the simplification, I get that this is equal to 1 by pi minus infinity to infinity e to the power I k x divided by k square plus 3 square dk. So, notice that again I can find the answer. I can find the answer by using residue theorem. Again, going back to our complex variables basics, the answer to this expression is that we have to again consider a semicircular arc and see that over the circular part the integral vanishes in the limit of these two values of this integral, and all I am left with is the real integral. And if we were to find the answer by the residue theorem, it is given by the following. So, this will be, so if I have let us say there are two cases now, right. So, I can have either x positive or x negative, right. It is an either or situation. So, if my x is positive, so in that case I have to find residue at the upper half plane, of the contour, and in that case my residue is at, so this will be at this following value k equal to 3i. Notice that I can factor this into k plus 3i, k minus 3i, right. So, the factor that gives me a positive root will be the one that contributes to the residue, right. And I get, calculating the residue, I get that f of x, so this will be f of x. So, f of x, because it is evaluated at x, so f of x is, after doing all the simplification, it is negative 3 e to the power negative 3x. So, this is for x positive, and similarly I can find for x negative, this is 1 by 3 e to the power 3x. Again, this will be by evaluating the residue at the other root, k equal to negative 3i, because the contour will lie, I am talking about the contour CR. So, this is real k, this is imaginary k. So, when we were to see the contour, this is the case when x is positive, and this is the scenario when x is negative. So, we have to appropriately take the residues plus 3i or minus 3i. So, if I were to combine these two results, I am going to get the answer to be f of x equals 1 by 3 e to the power negative 3 mod x, right. So, that is my answer to this problem. Okay. So, continuing, then I have, let me look at another case where I am looking at again the Laplace equation, which is given by this following equation uxx plus uyy. So this is Laplace equation in 2 dimensions, right? And again I choose my x to vary from negative infinity to infinity and y is from 0 to infinity. So y is non-negative and x is can take any value. And this time I choose my boundary conditions to be of the following form: uy at x comma 0 is f of x. So this is, in particular, we call this boundary condition as Neumann boundary conditions. So when I have a boundary condition in which the derivative is specified, that is a Neumann boundary condition. In one of the previous examples, we had the value specified at the boundary. So that is the Dirichlet boundary condition. So plus I have the other boundary condition as that u goes to 0 as y goes to infinity and x goes to plus minus infinity. So the decaying solution, the decaying boundary condition is as it is. Now the only difference between this example and say example 2, where we were using the Dirichlet condition, is due to this boundary condition, Neumann. So which means that if I were to choose my u to be of this form, so choose u of x comma y to be of the form integral v of x comma eta d eta. Let us say from, so the integration is from some arbitrary point to y, well, from 0 to y, because y is non-negative. So we can see that if we were to take the derivative will satisfy the Neumann condition, implying that this particular function v will satisfy the Dirichlet condition. So if we were to choose this as my solution, and if v satisfies the Dirichlet condition, then u satisfies the corresponding Neumann boundary condition, because u is the integral of v. So which means we have already found the solution to v. In particular, v of x comma eta is equal to eta by pi. Again, this is from example 2 that we have done earlier. So I get that this is v of eta x comma eta is eta by pi integral f of zeta d zeta divided by x minus zeta square plus eta square. So notice my variable y is replaced by this variable eta in the previous example. Okay. So I am going to substitute in this integral, and I am left with the following integration: u of x comma y is given by 1 by pi integral from minus infinity to infinity f of zeta d zeta integral from 0 to y eta d eta divided by x minus zeta square plus eta square. So I have just rearranged some of the integrals, and this is what I get. So I have that y is non-negative. Now this integral can be readily evaluated. We can see that this integral is with respect to eta, and I am going to get my answer as left in one integral from minus infinity to infinity integral of f of zeta. This is going to give me the following expression: this is log of x minus zeta square plus y square d zeta with a 2 outside. Okay, so further evaluation of this integral will depend upon what value of f is provided. So this answer can be left at this point, because we do not have further information about y. So before I move on to another example, I would like to mention possible exercises for the students that can be done along the same ideas that has been highlighted in these 4 examples. So in particular, the students can look at solutions to heat equation. Please see online what do I mean by heat equation. So, heat equation in, let us say, one dimension, in 1D with no source or sink. So, this is a very simple second order partial differential equation, and the same idea of Fourier transform can be used to find the solution to the heat equation. Or another exercise could be the solution to the wave equation. The wave equation in 1D. So, this can all be found out by the method just described and by the examples just described.